welcome to this course on algebraic geometry and commutative algebra. Last time I have left to prove Hilbert's basis theorem. Today I will prove Hilbert's basis theorem and some of its applications. So, today we will prove this is the theorem. This is called as Hilbert's basis theorem. I will also abbreviate by saying HBT. Say that let A be a Noetherian ring then the polynomial ring, the polynomial algebra infinitely many variables over A x1 to xn is also Noetherian ring. Okay, proof is very simple. There are several proofs available for this theorem and I am going to give the shortest proof, that is due to Sarges. So, first of all note that it is enough to prove the case n equal to 1, because then you can, by induction you can keep going for arbitrary many finitely many variables. Okay, in this case I will put B is the polynomial ring in one variable. So, I will just write the variable as x and we want to prove that B is a Noetherian ring. That means we shall prove that we need to prove that every ideal B in B is finitely generated. This is one of the characterization of Noetherian ring, that to prove a ring is Noetherian equivalent to proving every ideal is finitely generated. So, let B be an any ideal. Be any ideal in B. We may assume that this B is non-zero and B is also not the whole ring B. B is not a unit ideal, because in this case it is generated by the element 0, in this case it is generated by the element 1. So, we can, in both the cases it is finitely generated, therefore, we can assume this. Now, suppose B is not finitely generated. Then we should look for a contradiction. And contradiction to what? Contradiction to our assumption that the base ring is Noetherian. That is what we will hope to get a contradiction for. So, B is not finitely generated. Then what do we do? In B, so in this case choose a polynomial f1 in B such that degree of F1 is least. So, note that I am choosing F1 non-zero in B such that the degree of F1 is least. Why is it possible? Because we look at all the degrees. So, look at all the degrees of any F where F varies in B minus 0, and this one is a subset of natural numbers, and this is a non-empty subset because B is non-zero, B is not unit. So, we have to have some polynomial which is non-zero. So, this set is non-empty, and therefore, we use well ordering principle of n that any non-empty subset of natural numbers have the least element. So, I choose that. And now look at B minus ideal generated by F1. Since we are assuming B is not finitely generated, B cannot be generated just by this polynomial F1 because otherwise B will be finitely generated. So, this is definitely non-empty, and again choose F2 in B minus ideal generated by F1 such that degree F2 is least among the elements from here. This is again, note that F2 has to be non-zero because B has 0, but the ideal also has 0, so that is gone. So, F2 is non-zero. Note F2 cannot be 0. And we want to repeat this process. Now, next step will be take the ideal generated by F1 and F2 and remove that ideal from B and continue this process, and every time we will be able to choose a new element with the least degree least, that is because we are assuming B is not finitely generated. So, let us note what happened at the k stage. So, that means for every k bigger equal to 1, we have chosen, we have F2 Fk plus 1 in ideal generated by B minus in B minus ideal generated by the polynomials, earlier polynomials F1 to Fk, such that degree of Fk plus 1 is least among all the polynomials from here. So, this is what we have chosen. So, let us see how do the F1, F2 etc. look like. So, F1 will look like degree of, let us call degree of F1 to be D1, degree F1 to be D1. So, this one will look like some coefficient A1 F, not F, x power D1 plus lower degree terms. And F2 will look like A2 x power D2 plus lower degree terms. And what is the relation between F1 and the D1 and D2? So, degree of F2 which is D2, D2 has to be bigger equal to D1. That is obvious because F2 is also in B and so on. So, Fk Similarly, this is ak x power dk plus lower degree terms. And the fk plus 1 equal to ak plus 1 x power dk plus 1 plus lower degree term. Now I want to cancel this term. So d1, this is increasing sequence, dk less equal to dk plus 1. And if I have to cancel this term, I will supply the correct power of x to earlier polynomials and then try to cancel this. Okay. How do I do that? So first of all, note that if I look at, now somehow we have to use the assumption on the base ring that it is Noetherian. So look at the ideals in A, ideal generated by this coefficient A1, ideal generated by, the next one will be ideal generated by A1, A2 and so on, and ideal generated by A1 to AK containing ideal generated by A1 to AK plus 1 and so on. This is an increasing sequence, increasing chain or ascending chain of ideals in the base ring A, ascending chain of ideals in A, but A is Noetherian. So therefore there exists a stage K, from that onwards it will be equality. So I will write here, there exists K bigger equal to 1 such that it will be equality onwards, equality here, and all the way it is equality. That is because A is Noetherian. But now what is more important is AK, this ideal equality is important, is AK plus 1 is here. So this AK plus 1 should be linear combination of the earlier one. So that is B1 A1 plus BK AK for some B1 to BK in the base ring A. This is what happens. Now I will use this B1 to BK and F1 to FK to cancel this term. So how do you do that? Let's go. So now what you do is you multiply F1 by B1. Look at B1 F1 plus BK FK. No, I have to supply some power of x. So let us write more precisely. B1 x power, I have to make power to be dk plus 1. So I have to make here dk plus 1 minus d1, that is F1, plus B2 x power dk plus 1 minus d2 F2 and so on. Consider this polynomial. Bk x power dk plus 1 minus dk Fk. Look at this polynomial. Let us call this polynomial as G. So first of all, note that I have to subtract it from here. From here you subtract Fk plus 1, or from Fk plus 1 you subtract, that doesn't matter. Call this as G. Then what is the leading term of Fk plus 1, that is Ak plus 1. And what is the leading term here? This is minus. What is the leading term here? B1. So now all these terms have become degree dk plus 1, because F1 has degree d1. This so the leading term will be B1 times leading coefficient of F1, that is this. Similarly B2A2 plus BK AK and minus this. But we have written AK plus 1 as this, so this is 0. So that means this is the coefficient of, this is precisely the coefficient of x power dk plus 1 in this, that is precisely this is 0 in G. Therefore degree of G is strictly smaller than dk plus 1, and where is G? And G, I claim first of all that belongs to B, that is no problem because all these Fi's belong to G, and it cannot belong to ideal generated by F1 to Fk, because if it does, this side is already belong to this. So if G belongs, so let us write explanation for this. If G belongs to ideal generated by F1 to Fk, then F will also belong to the ideal generated by F1 to Fk, not Fk plus 1, because this belongs already. If this belongs, this will also belong, but that is a contradiction to the choice of. So this is a contradiction to the choice of Fk plus 1. So therefore we have checked this. B cannot, G can. On the other hand, degree of G is strictly smaller. On the other hand, degree of G is strictly smaller than degree of Fk plus 1. This also contradicts the choice of Fk plus 1. This also contradicts the choice of Fk plus 1. So either statement contradicts the choice of Fk plus 1, that means something wrong with our original assumption that B is not finitely generated. So this proves that the ideal B must be finitely generated. And hence the conclude the proof of the theorem. This is really very simple. Okay, all right. So now I will write few corollaries to this, few consequences. So consequences HBT. There are many consequences of this HBT, as I was saying in the last lecture, that Hilbert proved this theorem to prove some existence of some invariants, and this was much easier than the existing proof then. So first of all, some corollaries. Corollary 1, let A be a Noetherian ring. Then every A algebra of finite type over A is also a Noetherian ring. Proof: if B is a finite type, if B is an A algebra of finite type, what does that mean? That means, so that is B is, there exists a surjective A algebra homomorphism. From the polynomial ring in finitely many variables to B. This is A algebra homomorphism and surjective. And now we know, we have noted this earlier, that means this B is a quotient of the polynomial ring in finitely many variables, and we know therefore there is a one-to-one correspondence between the ideals of B and the ideals of the polynomial ring which contain the kernel of this map. So, if I call it phi, if I call this as phi, then the ideals of B and ideals of the polynomial ring in these n variables which contain, A contains kernel of phi, this set and these ideals, that is a bijective correspondence. But these ideals are finitely, in fact all ideals here are finitely generated. These ideals are finitely generated, therefore ideals of B are finitely generated, and therefore B is Noetherian. So every ideal in B is finitely generated and hence B is Noetherian. Okay. So also, so corollary 2, every K algebra of finite type where K is a field, or okay, I will write that separately, is a Noetherian ring. Okay, so another corollary which I will be very important. See, this corollary is very important for remember when we introduce affine algebraic sets, and then we say that every affine algebraic set is defined by finitely many equations. So this is very important. I will note that also later, but let me note another one which is also very important. Every finite type Z algebra is a Noetherian ring. Because Z is Noetherian, in fact Z is a principal ideal domain. So therefore this corollary actually one should write, instead of Z, replace it by any PID. Any PID. every finite type algebra over a PID is also Noetherian ring. Okay. So, that is these two. Okay, now all right, now this is for the recall that what we have in this setup. When you have a field extension L over K, field extension, then what was affine K algebraic set in L power n. This was precisely V L of an ideal A, where A is an ideal in the polynomial ring in n variables over K. Ideal. That is affine algebraic, that is what this K algebraic means. The equations, the ideals are in the polynomial ring over K. And also we have noted that actually we may assume even A is a radical ideal. That is not so important right now. What is more important, what I am saying, that because this A is an ideal in the polynomial ring over a field which is Noetherian by HBT, therefore this A will be generated by finitely many polynomials. So, that is F1 to Fm by HBT, where F1 to Fm are polynomials with coefficients in K. What does that mean? So, let us write down this over this. What does it mean is, that means V of A, VL of A is same thing as VL of these finitely many polynomials. We have noted that this depends only on the ideal generated by F1 to Fm. And what is this? This is all those points A equal to A1 to An in L power n, such that Fj of A1 to An is 0 for all j from 1 to m. So, sometimes you will also see in a classical algebra geometry books that one says that the affine algebraic set, K algebraic set, is defined by this equation F1 equal to 0, etc., etc., Fm equal to 0. This is not very good notation, but that is how classically it was written, because vanishing common zeros of these polynomials are precisely the points in the affine algebraic set defined by ideal generated by F1 to Fm. So, see, this one cannot write, because one side is the polynomial, other side it is 0. What it means, abuse of notation means, this is the common set of zeros of these polynomials. So, this was what Long proved. So, henceforth whenever we want to study affine K algebraic sets, we can always assume that it is defined by finitely many equations. Now, the next questions will crop up, how many equations are really needed to define, and that is more serious questions, and even till today it is not completely settled. There are some partial answers. When time comes I will keep commenting on this, but right now I will make one example to show you that. So, let us make an example. example. So, in other words, this VL of F1 to Fm is intersection of M hypersurfaces. This I have been saying it. So, now the question becomes, given an algebraic K set, how many hypersurfaces are needed to get the given algebraic set. And this example shows that if the ground field is not algebraically closed, then this question is not so interesting. For example, okay, so let me write what I want to write. So, let okay, I am in the case, the classical case. Classical means okay, L equal to K. So, we are only considering K algebraic sets in the affine space over K, and I am assuming K is not algebraically closed. Then let us see what happens. Then every K algebraic set in K power n is defined by one equation, that is, it is an hypersurface. So, I am not going to prove it here completely, but I am going to give a sequence of arguments in the assignments, and one of the crux of that assignment is the following statement. So, this follows from the following, let me say, following exercise. So, given any natural number n bigger or equal to 1, there exists a polynomial f of, let me write now, x1 to xn in k x1 to xn, and again stress here k not algebraically close. For example, K equal to Q or R or any finite field. Such that V K of F, there is only one 0, namely 0 0 0. Origin is the only 0 of this polynomial f. So, and let me also say that in case of real numbers or rational numbers, it is really very easy, because you can simply, if k equal to q or r, then you can simply take f equal to x1 square plus x2 square plus xn square. The only 0 of these polynomial is 0 0 0 0, there is no other 0, which is very clear for Q and R, that is because of the order. The squares are positive always for any, if you have any n real numbers, then the squares of sum of the squares of these real numbers is always positive. So, it cannot become 0. Alright. So, for finite field one has to work out little bit, it is not so difficult. I will say do it by induction on n, and more hints I will write in the exercises. So, with this I will end this first half of this lecture, and we will continue after the break about some more consequences of HBT for modules, and so we will meet after the break. Thank you.